Welcome back everyone to this lecture on neural networks. So we just learned about a single perceptron. However, a single perceptron model won't be enough to learn complicated systems. Fortunately, we can expand on the idea of a single perceptron to create a multi-layer perceptron model, commonly known as a basic artificial neural network. We'll also introduce the idea of activation functions, which we'll cover in a future lecture. So how do we actually build out a neural network from the idea of a single perceptron? Well, it's actually quite simple. What we do is we simply build a network of perceptrons where we connect layers of perceptrons using what's known as the multi-layer perceptron model. Essentially, we have a vertical layer of these neurons, these single perceptrons, and we take their outputs and then feed them to the next layer of perceptrons so that the output of the previous layer becomes the input of the next layer. And you'll notice here that every neuron, at least in this illustration, is connected to every neuron in the next layer. And this is known as a fully connected layer. We'll learn about different types of layers and different network configurations like recurrent neural networks and convolutional neural networks in future sections of the course. But right now, we're just focused on a feed forward, that is to say that all the information is going from the input layer all the way to the end to the output layer, and it's fully connected, which means every neuron in one layer is connected to every neuron in the next layer. So the outputs of one perceptron are then directly fed as inputs to another perceptron. And you'll notice I've begun to kind of switch the words perceptron to neurons. And it's up to you which one you prefer, but when we're in general discussing neural networks, we'll start to lay off the single perceptron terminology and then use the more flexible neuron terminology. So from now on, you'll probably hear me say neuron a lot more than single perceptron. So basically, this allows the network as a whole to learn about interactions and relationships between features. So the first layer coming in is the input layer, and this is the layer that directly receives the data. And this could be things like tabular data that has features on information that you're trying to predict a label off of. The last layer is known as the output layer. And keep in mind, even though this illustration just shows one neuron in the output layer, this last layer can be more than one neuron, especially when we're dealing with things like multi-class classification. Then, any layers in between the input layer and the output layer are known as hidden layers. Hidden layers are difficult to interpret due to their high interconnectivity and distance away from known input and output values. So the input layer, that's really easy to interpret because that's directly accepting the inputs of the raw data that you already know and understand. The output layer is also a little easier to interpret since it's closely associated with the label that you're actually trying to predict. The hidden layers, especially as you have a deeper and deeper network with more and more hidden layers, those become more and more like a black box, since for really large networks, it's difficult to understand what a single neuron is picking up as far as the interconnectivity of the last layer and the next layer. So, a question students often ask is, when does a neural network become a deep neural network? And really, the terminology is quite simple. You have a deep neural network when you contain two or more hidden layers. So here we can see on the left-hand side, this network only has a single hidden layer. You'll notice that the hidden layer is quite wide, meaning it has quite a few neurons. So the width of a network is how many neurons are in the layer, and the depth of a network is how many layers there are in total. So a deep neural network is two or more hidden layers. So again, to overview the terminology, we have the input layer, first layer that directly accepts real data values, hidden layer, any layer in between those input-output layers, and if we have two or more, we begin to have what's known as a deep neural network, and then the output layer is the final estimate of the output that the network estimates. Now, something that I find really incredible about the neural network framework is that it can actually be used to approximate any continuous function. And researchers Liu and then also later on Boris Hanin proved mathematically, in the same way you would have a proof of geometry, that neural networks can approximate any convex continuous function. So for any convex continuous function, essentially a function that you can continually integrate over, there should be somewhere out there some network that can directly approximate that function. And while you can't maybe find that network directly, and it may take quite a bit of time before you train a network, find the right number of neurons and the width and depth, there theoretically, and it's been proven mathematically, there is some network out there that can actually approximate that function. So for more details on this, since the scope of that proof in the mathematics is outside the scope of this course, and it's not really important that you understand that to actually build out these neural networks, you can check out the Wikipedia page for Universal Approximation Theorem. It's a really cool page. I definitely encourage you to check it out. But that page basically discusses in more detail how those mathematical proofs actually work. And what's really cool about a lot of those mathematical proofs is there's even proofs on placing restraints on the width in order to match up to the inputs of the continuous function. And you can still prove mathematically that there is some network out there, even with those constraints of the number of neurons with in that network that will still approximate that continuous function. So definitely something I encourage you to check out if you're interested in that. Now, previously, if you recall, in our simple model of the single perceptron, we saw that that single perceptron, that neuron, if you will, it contained a very simple summation function. We essentially took our inputs x, multiplied them by their own weights w, and then we added that neuron's bias and summed it all up. However, in most use cases, we really don't want to just do a straight sum. Instead, we're going to want to be able to set constraints to our output values, especially in classification tasks. So you can imagine in a classification task, it would be really useful to have all the outputs fall between 0 and 1. And then these values can present the probability assignments for each class. If we just have a large summation, we have no upper limit on what values can be. So you should already start thinking of, well, what kind of functions can we apply to those inputs times the weights plus the bias in order to put constraints or upper and lower limits on what the neuron value will actually spit out. And that's where activation functions come into play. So in the next lecture, we're going to explore how to use activation functions to set boundaries to output values from the neuron, instead of just summing everything up like we did in that simple perceptron model. And there's a wide variety of activation functions, which is why we'll have an entire lecture on it. So up next, we're going to talk about activation functions and a few options you'll have. We'll see you there.